Now it's recording. So let's go ahead and get started. If I can find the PowerPoint. Here it is. So today we're starting a unit on light. And to be perfectly honest, there's a lot of material in today's lesson. It's probably going to take the whole period to get through. And a good bit of it is probably going to seem a little scatterbrained. Because we're just kind of covering a large breadth of material in not a long amount of time. So, light. Light is the fastest moving, at least currently known, phenomenon in the universe. Travels at 300 million meters per second. I'm going to give you a second to sit with that number, 300 million meters per second.
Why does it say currently? Because had that speed changed? Oh, because that's something been ever faster?
There could be something discovered that might be faster, but as of now, this is what we're calling the fastest. While the exact characteristics and composition of light aren't known, currently we kind of clump it into two categories. We know that light has some electromagnetic wave properties, and light has some properties that make us think it's a particle as well. Okay, in terms of the properties, when you heard an echo, we said that was the sound doing what?
Coming back.
Start with an R.
Reflecting.
Okay. If there's an echo, that's the sound reflecting. So in other words, waves reflect. They can also refract. They can diffract. So reflection, refraction, and diffraction. Those are all properties of waves. And light does those. Okay. So light will reflect, refract, and diffract. So those are properties that lead us to believe that light is some sort of wave. Okay. However, light also has some properties of a particle. So, for example, with the photoelectric effect, I don't know if y'all are familiar with that, but a photon of light can come in and strike an electron, and it strikes that electron, gives it some kinetic energy, and that would make the electron move and generate current. If there's not a particle moving that's striking it, it's kind of hard to give it kinetic energy if it doesn't have kinetic energy itself. Okay, so that leads us to believe that light also has some particle-like properties. So for me, that's kind of confusing. It has wave-like particles properties. It has particle-like properties. So we're kind of settled with it's kind of both. Okay, that's called the particle-wave duality of light. It's kind of mysterious. A little bit of both.
We know it exists.
We know it exists.
Why can't I just make up a new word and call it that?
Huh?
It's called this.
It's called. There is a new word. It's called an electromagnetic wave. So we said. So up here we said light is an electromagnetic wave. Let's step back a second. I'm going to give you a definition of an electromagnetic wave. An electromagnetic wave, guys, is okay. But before we get there, let's think. Okay, a typical wave cycles between things, right? So like a sound wave cycles between high pressure and low pressure. A water wave cycles between being high and a crest and a trough, being high and being low. A seismic wave has cycles. Okay, so an electromagnetic wave is going to have cycles as well. Okay, and it's going to cycle between two different things. Okay, it's going to cycle between electric fields, so a positive, negative, positive, negative, positive, negative electric field. And it's going to cycle between magnetic fields. So north, south, north, south, north, south.
Simultaneously?
Simultaneously. Okay, so if we graph that out, what we get is this. Okay? And that looks really daunting and really confusing. Okay? I prefer to look at one graph at a time. Okay? So my preferred drawing of an electromagnetic wave. I'm gonna bring that back up in just a second, guys. I can't see. Okay, so the way I like to think of an electromagnetic wave, guys, is we have two components. Kind of, with sound, we graphed out pressure. The pressure went high, pressure went low. Okay, with electromagnetic wave, we're going to graph out two things. Okay, the first thing I'm going to graph out is the electric field. Okay, so the electric field is going to oscillate between positive and negative polarity. So this is an electric field. Okay, and then I have another field, a magnetic field, that's going to oscillate between a north and south polarity. And for some reason, guys, we represent magnetic fields with the letter B instead of M. I don't make the rules. So that picture that you saw a second ago, that three-dimensional picture, okay, is essentially just take those two graphs that I had and put them into one graph. Okay, so I have three axes there. One of them is going left and right. One of them is going up and down. Okay, that makes sense.
Is there a reason for it being diagonal?
Diagonal.
It's just showing you.
It's just different axes. Think of it like I've taken these two and now I've made a three-dimensional plot. So one of them is going and one of them is going.
Okay.
And they just kind of superimpose those graphs. Okay? That makes sense? Okay. So for me as a student, I looked at that picture, and a lot of physics teachers don't like to explain kind of what's going on there. Don't think of that as particle movement. There aren't two things moving. This is just, in the same way that a sound wave is high pressure, low pressure, high pressure, low pressure, this is an electric field that's positive, negative, and a magnetic field that's north, south, north, south. Okay? So if I'm a particle and there's an electric field coming past me, if there's an electric field coming past me, then what I'm seeing is positive, negative, electric fields coming past, okay, and north-south magnetic fields, okay. That makes sense. So it's a wave that's traveling in photons. Huh? It kind of feels like I'm saying something really deep.
I'm done.
All right. So an electromagnetic wave, guys, is not a mechanical wave. So since an electromagnetic wave is not a mechanical wave, it does not require a medium. With a sound wave, if it's traveling through air, in order for us to know that there's a sound wave moving, we see we feel the effects of air particles moving. With water waves, we could see the water molecules moving. And so electromagnetic waves are a little bit tricky because since it doesn't require a medium, that means nothing's moving. Okay, so in terms of detecting electromagnetic waves, if it doesn't hit you, you can't see it. Okay? There's no way of detecting an electromagnetic wave that does not impact you. So if you're out in space and a laser you have a laser and it whizzes by you, unless that laser is pointed right at your face, then there's no way of detecting that that laser is there. Okay? I mean, you can detect you can see the device, but there'd be no way of detecting the light from that. Okay?
Could you feel it?
So you can't even see it. So you can't even see the light. The laser.
Only if it hits you.
Has nothing to do with it. It's like
It has nothing. I mean, unless there's a mirror. But in Earth, the way we see that beam is by the air molecules scattering it.
Oh, so like a flashlight, you can see the beam and then you see where it hits. But in space, you can only see where it hits.
You can only see where it hits.
Oh,
Okay. What now?
Unless you point the flashlight at yourself, you're not seeing the light.
Yes. Yeah.
What about the sun? You see that?
Those beams of light are coming towards you. They're hitting you. All right. So since there's no particle movement, to me, I say, okay, well, if there's no particles moving, then how does the wave move? Okay, because if there's no particles moving, then what's moving? Because that's kind of getting crazy stuff here.
So wait,
This is the fun part.
so the sun beams are electromagnetic?
That's electromagnetic. Yeah.
Okay, so if we can't see it or feel it, why do they say don't stare at the sun?
Because it's coming straight at you. I mean, you can. It's like me pointing a flashlight right at your face. You can see it.
What
But
happens
if we're in space and I point a flashlight over there, you can't see it. Huh?
Like, yes, people say don't stare at the sun because it's going to, I guess, deteriorate your vision, but why?
What happens to a apple if you leave it out in the sun?
Dries up,
Okay. What happens to a pot of water if you leave it out in the sun?
vaporize,
What's in your eye?
water.
So there are other things there, but that
Yeah, you're
they're more complex. But yeah, it's very not good for your eyes. All right, all magnetic waves, guys, are created by vibrating electric charges.
Mad person, I'm kind of happy.
There are more complex ways of creating electromagnetic waves, but we're just going to pretend like this is the way to do it. Okay.
I tried to get back, I just laugh it off.
The very basic precept you need to understand, guys. If I have an electric charge that moves, okay, a moving electric charge generates a magnetic field. Okay, so if I hook up a wire to a battery, both ends of the battery, and electricity goes to that wire, then it makes a magnetic field around the wire. Okay, because those are electric charges moving. Okay, and since we just said the particle's vibrating, it's moving back and forth, then I would assume that that makes a changing magnetic field. That makes sense? Okay, so I have a vibrating electric charge. That makes a changing electric field because vibrating charges make changing electric fields. Okay? Eh?
Yeah, that's
Really? Just eh?
So when you hook up a battery, or something else using a wire, the electricity's not just going from the battery to blood, it's going back and forth because it's creating a circuit, right?
No. If it's just a DC circuit, and I plug up wires to both sides of the
Both sides of the battery?
If I hook a wire to this side of the battery and a wire to this side of the battery, current's going to flow through the wire. I mean, you ruin the battery pretty quick, but you just hook it up, current's going to flow through. A magnetic field will be generated around that wire.
But why is it changing?
Huh?
But why is it a changing magnetic field?
It's not a changing magnetic field. If I take the wire and if I flip the terminals back and forth, then that would be a changing magnetic field.
Okay, so then when is
So
it
I have a vibrating electric charge. In other words, it's going back and forth, then that generates a changing magnetic field.
What's an example of a vibrating electric charge? What?
Remember we talked about heat? We said as you heat an object up, it tends to
Expand.
something else.
faster.
And it tends to move faster, right? In a solid, how does it move? It vibrates, right? Okay, so I mean with a light bulb. Okay, in a light bulb I have a little filament. It's made out of metal. You take that and you put current across it. That makes the particles vibrate. And those particles, when they vibrate, they put out light. Okay. Alright. So since particles are not moving in the same direction, they're vibrating, that generates a changing magnetic field. Okay? A changing magnetic field induces a changing electric field.
Hey, I have a question. It might be dumb. What's a magnetic field?
You're holding a magnet. I'm holding a magnet. There's a magnetic field between them.
Standing in a field.
So, how?
So a changing magnetic.
So does that mean like whenever the lights are on, there's a magnet going on or something?
What now?
The lights are there for the
I'll give you a little drawing. Let's say I have an object over here, and it's going to generate a changing magnetic field. If I have a magnet here, and we'll put it on a little pivot point so it can spin. Okay, it can freely spin. I'll have a north and a south side. Okay, every magnet has a north and a south side. So this object is making a changing magnetic field. When this is a north here, this north is going to want to flip around. So it's like this, right? Well, it's going to change to where it's the south now. It's going to flip back around to that. So this changing magnetic field would make a little spinning thing there. Okay, so that'd be a changing magnetic field. Changing electric field would do the opposite. Well, not the opposite, but it'd do something else. If I had a proton here, okay, well, while this is positive, it's going to want to move away. Well, while it's negative, it's going to want to move toward it.
She was asking us what is magnetic field. Like not
Okay, a magnetic field.
What is a magnetic field? What's the purpose of one?
What is the purpose of one?
What is the purpose and what is
What? Okay. A magnetic field is exactly the same as a gravitational field.
Okay, because I was wondering if everything's pulling, then how is it different than that?
No, it's very exact same concept as a gravitational field. It's just
Different thing.
force. You can think of it as a magnetic force field. So magnetic force.
force fields exist?
What now?
Force fields do exist?
And always
Sure.
God, say
Yeah.
And
Gravity is a force field. So since guys, since changing magnetic fields induce changing electric fields, and changing electric fields induce changing magnetic fields, then they just kind of carry off of each other. Okay. So that magnetic field's changing. That makes the electric field change. The electric field change makes the magnetic field change. And so they just go on and on and on and on. Okay, and that's how an electromagnetic wave is created. Yeah. I this is probably a little fuzzy. But here's my way of thinking of it. You know, we started these two slides with the question of how does an electromagnetic wave travel if there's no particle movement? It travels the exact same way as if I put a magnet here and a magnet here, well, they're going to get attracted, and there's no particle movement between them. That magnetic field travels from one of them to the other one, or together. I don't know how it travels. It travels though. Okay. So it travels in the exact same way that travels. And it travels the exact same way that the gravitational field travels. Okay, it doesn't go through anything, it just kind of does. It just travels. Okay? We see electromagnetic waves everywhere, guys. Light is a very, very small spectrum of what we utilize in the electromagnetic fields. Okay, so light, radios, cell phones, TV signals, over-the-air TV signals, remotes like TV remotes, microwaves, Bluetooth, Wi-Fi. Okay? Those are all electromagnetic waves. And fundamentally, they're all exactly the same as light, we just can't see them.
Like in their properties.
Huh?
Like in their properties.
They're the same way as light in the way that a 30,000 hertz tone is the same as a 16,000 hertz tone, just sounds different. Can't hear it, but it's just different. You know? Okay, so one example. One example is a remote. Okay, most remotes use something called infrared to transmit signals, and so I want everybody to look really closely. At this infrared remote, we'll see kind of a little shiny spot. I don't know if y'all can see it. I want you to look and see the light that comes out of the infrared remote. Y'all see it?
Yeah.
The answer should be no. Okay, you shouldn't see any light coming out of it.
Saw something like white reflecting out.
No, yeah, you shouldn't see that. Okay, however, guys, take out your cell phones and turn on cameras.
Take off my cell phone.
Take out your cell phone and turn on the camera.
It's already up.
Okay, and it won't work if you have an iPhone 5.
What? Oh.
So, okay, take out your cell phone, turn on the camera, and just kind of face it up here.
Do we look through the camera?
Look through the camera at the remote.
I don't see any.
Do they have to zoom in?
What do you see?
It's blinking.
Oh,
Hold up.
That's cool.
Oh my god.
That's depressing. The one thing I can't do.
Okay, so for those of y'all who aren't seeing that, I can put it under here as well. Okay, we don't through your eyes you don't see anything. However, through a camera, okay, we can see that infrared light is being put out. Okay.
So that's because the iPhone 5 is protecting you from epilepsy.
Well, the iPhone 5 has an infrared filter, so it filters that out. And some cameras have them, some don't. So what we're seeing here, guys, is the exact same camera that is picking up visible light that we see is also picking up electromagnetic waves we can't see. There's no difference between the properties of this, which you can't see, and that you can see. Okay? That makes sense.
Does the receiver flash as well?
The receiver?
Yeah, on the infrared waves.
No. And to transmit signals, all this does is essentially modern day Morse code. It just transmits do. That means turn on. Okay. It just sends different flashes mean different things.
What does this flash do?
As far as this is going on YouTube.
Okay, so
I can't see.
like I said a second ago, guys, light is a very small band of what we call the electromagnetic spectrum. Okay, our eyes are only capable of detecting a very, very small band of all the electromagnetic waves. Okay, so gamma radiation, ultraviolet, TV signals, radio waves, okay, all those are fundamentally exactly the same as light, however, our eyes can't pick it up. And when I say a small band, this would be the electromagnetic spectrum. Okay, notice if this is all categorized by wavelength. Notice over here at gamma rays, we're at 10 to the negative 14th. Okay, and then we move up through AEM, which is 10 to the 6th. So we're kind of looking at a breadth of 10 to the 20th in diversity there. Okay, 10 to the 20th. That's a huge amount of diversity. We can see from like 380 to 780. Okay, so we don't even see like a full 10 to the 1. Oh, we do see 10 to the 1. We don't see a 10 to the 3rd. Okay, so we're seeing an extremely small deviation. Okay, of the electromagnetic spectrum. Okay, so you know these radio telescopes that they have, that are picking up, these huge. I mean, they're just picking up a different spectrum of the electromagnetic radiation. Okay, sometimes different spectrums of the electromagnetic radiation might travel better through clouds of dust. So they'll say, okay, well, we'll look through this type. And sometimes light may travel better, sometimes longer wavelength, sometimes shorter wavelength. Okay, and so they can use those properties to kind of see images for whatever's the most appropriate. Okay, so that's how we see the surface of Venus. I mean, we can get an approximate image of the surface of Venus. We've never been on Venus. There's never been a probe on Venus, at least as far as I'm aware. But I mean, what we can just do is say, okay, what spectrum will go through the atmosphere of Venus? Okay, we'll use that one. And just use a camera that picks that up. Okay? Or the camera equivalent. So light, guys, is part of this electromagnetic spectrum. We categorize it by wavelength, but also by frequency. Most commonly, we use wavelength. Right at the limits of what we can see, we're going to have infrared and ultraviolet. Infrared, being what we use in the TV remotes, we can't see that. Ultraviolet being what burns your skin if you get a skin burn or skin, sunburn. Yeah, that thing. Skin cancer too. Looking up at this spectrum, guys, what looks the brightest to you? What color? Yellow. I mean, yellow looks the brightest. In terms of intensity, you think that yellow up there is any more intense than any of the other colors? No. Okay. It's no more intense. So why do you think yellow looks brightest to us?
That's the only thing we can see.
First of all, it's kind of in the middle of the spectrum that we can see. Okay, but also, guys, if I take the sun and I graph the colors of output of the sun, what we would see is kind of a bell curve. And at the top of that bell curve, the highest output of color would be yellow. Okay, so current theory is that, well, the human eyes just developed to see yellow the best because that's the most abundant color or the most high intensity color put out by the sun. So kind of interesting.
When they do car lights, like some of your car lights are yellow and your brake lights are red because you see that usually in the cop cars or blue.
Yep. Same thing, like newer like emergency vehicles. What color are they making them now? Oh, they're making them yellow. Okay. A lot of the newer emergency vehicles have a lot of yellow on them. If you look, it's just what now?
I heard purple is like the most attractive light to your eyes.
That was red.
That was green.
I don't know about that.
Red is like seductive.
I was driving down the street and there's a big purple light.
Seductive, man. If I said red, I'm
Yeah, that's a good point.
that red dress. You got red bubble gum in your
Okay, so we said that light kind of has two properties. It has kind of the particle-like property and the wave-like property. So since light has wave-like,
I didn't get the last few words.
wait, we got to move it. It'll be on mine.
Why you going?
So since light behaves as a wave, it's going to follow that wave equation that we have so far, the V equals F lambda. Okay, for light, that V, that speed, is 3 times 10 to the 8th meters per second. In empty space, however, that's going to deviate just a little bit, depending on if it goes through a medium. General rule, the more dense the medium, the slower light goes. Okay? So air, it's going to zip right through, no problem. Glass, it's going to slow down a good bit. Water is going to slow down a good bit. Bricks, it's really, no, it's not going to travel through bricks. It's going to, It's going to reflect off of it.
Here's like you shouldn't be here.
Not very much.
It get absorbed. Some of it will get absorbed. That's why bricks get hot if they're sitting out.
Is that watching? I was gonna ask watching. Like, why does the light bulb get hot?
Because remember, just a second ago, we said in order for that light bulb to produce energy, it's vibrating the.
So that creates energy.
But the way that they get those to vibrate is by heating them up.
Yeah,
So-
I mean, for the Marines.
Okay, so guys, that decrease in speed we're going to attribute to the time it takes to be absorbed by molecules. And so don't worry about that image or those words too much. I'm going to give you a little picture. What I think about, guys, is light in any empty space travels at 3 times 10 to the 8th meters per second. However, when it hits something, it has to be absorbed and retransmitted. It can't travel through things. Okay. So let's say I have some baseball players and they want to throw a ball from here to over here. Okay, obviously the fastest way to get a ball from here to here is a direct path, right? And he missed, but whatever. Would be a direct path. Okay, and light, if we're using our light analogy, it would follow this direct path at 3 times 10 to the 8th meters per second. Okay, however, if this distance is too long, we might need to have 3 or 4 baseball players in there. Okay, so he throws to him, and we'll say she, throws to him. So when we have these players in the middle, do y'all see how the process kind of gets interrupted? Okay, I mean, between each one, we're traveling at 3 times 10 to the 8th. Okay, however, it has to be caught, it has to be thrown again. Okay, same thing with light. Okay, the closer these are together, the more delays it has. So for something that's really dense, there's lots of delays and it tends to move slowly. And for something that's not dense, it goes right through without too much problem. Okay, that explains why if light goes through glass, it comes right back out right back out the other side at 3 times 10 to the 8th meters per second. If it wasn't going the same speed between molecules, then it would come back out the other side at whatever speed it was going through here because it lost kinetic energy. Okay, however, since it goes the same speed, but it always travels at the same speed. Okay, so it's always going to go at 3 times 10 to the 8th meters per second. Make sense? Okay. Now you might say on average through here it's traveling slower. It's not traveling slower, it's just moving slower. That makes sense? Huh? In the same way, let's say you're driving at 30 miles per hour. Okay, the speed you're going is 30 miles per hour, but you have to stop every 100 yards. Okay, well, when you calculate your average speed, you might get 20, but you actually drove 30. So here, when we calculate the speed of light in glass, we're going to calculate lower, but it's actually moving at this speed. It's calculating lower because it had all these delays, but it's moving at 3 times 10 to the 8th.
So does light have to speed up to its normal speed, or does
No.
it like
There's no, okay, well,
it just automatically
the photon is a massless particle. So since the photon is a massless particle, it doesn't have to follow the rules of acceleration. It just
goes
like that.
But when you're saying it goes, that implies that you're seeing something moving, and the problem is when we're looking at light, it's not this kind of visual something moving. It's really, it just does. It's not so much. It's kind of hard to explain.
So it does not have to speed up and slow down.
No, it does not speed up and slow down.
Okay.
There's no acceleration of light. Okay. Other really interesting fact about light. Light. We've already talked about this. I don't want to talk about that yet. Light. Oh, light. The speed of light is not relative. Okay, our speeds are relative, and what I mean by relative is, you relative to me, we're not moving. Relative to the sun, we are moving. Okay, so in other words, my speed is different depending on how you measure it, right? Okay, the speed of light is not relative. No matter how you measure a light wave, it's always the same speed. Okay, so therefore, if I have
Because if it's there, then it's going to speed.
okay. So if I have a chica and an airplane here, and a beam of light passes past the airplane. Let's say the beam of light is going 3 times 10 to the 8th. We know that's the speed. If she's going at 2.99 times 10 to the 8th, so in other words, right up near the speed of light, when she measures the speed of light, she's still going to measure 3 times 10 to the 8th. Okay? If it were relative, she would measure 0.01 times 10 to the 8th. Right? If it were relative, that's what she would measure. That's not what she measures. She still measures 3 times 10 to the 8th. And if there's somebody down here, hombre, then he's going to measure 3 times 10 to the 8th as well. Huh? Hombre means man. What's...
You should read
It's
the,
just really funny.
read the comments in the video. There's a lot of Spanish speaking people down there.
Yeah, there were some requests. More Spanish words, please. Okay, so no matter what observer, they always observe at 3 times 10 to the 8th. And that's caused by something called time dilation and length contraction, but we'll talk about that later. Huh? Yeah, it is. Okay. So light, guys, is scattered in 2 different ways. We can either make light. So in other words, vibrating particles, that would be a luminous source. Okay, so the sun, a flashlight, a laser beam, lights in the ceiling. Okay, make light. Okay, or you can reflect light. Illuminated source. Okay, so the moon would be an illuminated source. The moon does not make any light of its own. Okay, it reflects the light from the sun. You and I, we are illuminated sources. The only way I see you is that you're reflecting the light from that light up there.
That's not really right.
So you don't produce our own.
We do not produce our own light. No.
I need me a brown.
But some fish do.
Some fish do.
Grace, are you a fish?
They're not really. Alright guys, then we're going to measure the intensity of light 2 different ways. The first way is by the total amount of light given off. Okay? That is called the luminous flux, and it's measured in lumens. Okay, the luminous flux doesn't change. Okay, it doesn't matter how far away you get from the object. It doesn't matter how much of the object's light's hitting you. It doesn't matter any of the object's light's hitting you. The luminous flux is always the same. In our solar system, what has the highest luminous flux? The sun. Okay, that's measured in lumens. So when you go to a store now, if you want to buy like an LED bulb, they don't really give you the brightness in watts anymore because that'd be kind of confusing. They give it to you in lumens. The lumens on that projector, I believe, is 2,000. So just kind of give you a number to work off of. So that's about 2,000 lumens here. Huh?
How many lumens is the sun? A bajillion, 900,000?
Yeah, something crazy. All right, and then the second way we measure the intensity of light is kind of like the scene intensity. This is like how intense does it look? Okay, and that's the illuminance. It's measured in lux.
It looks really bright.
Okay. So, question, guys. The sun is the highest, does have the highest luminous flux in the solar system, but does the sun have the highest illuminance in the solar system?
No.
Depending on where you are, okay? If you're right next to the sun, yes, it probably does have the highest illuminance in the solar system. But from Pluto it doesn't have much illuminance. Okay. I mean, if I take this laser beam outside and I shine it on the ground, I mean, I can see the beam. I mean, this laser beam technically would have more illuminance than the sun would, because the sun's not overpowering it. Okay. But I mean, it doesn't have anywhere near as much luminous flux. Okay, that makes sense. All right, guys, grab a partner to talk about.
Grab a partner, go shoot over.
They reflect the light over other things. What is the difference between visible light and ultraviolet waves?
Like television signals over the air. Huh?
Oh. As we look deeper and deeper into space, what do you think we are seeing?
What you're seeing is later on because they
The reflection. The reflection of light. The reflection. Like we are seeing the light given to us, which are light.
well, the sun's a lot more recent because it's a lot closer. The stars like saying
Like Jupiter's a star.
that's a few
I
thousand.
mean, like it appears to be a star when it's in the sky. That's why it's giving off.
That was probably a lot longer.
It does. It's a star.
All right, guys, let's talk through these. How are your eyes capable of seeing things that do not create their own light? Okay, they reflect light. That's the reason why if I turn the lights off, do you see anything?
Yeah.
Yeah.
Well, if I turn the lights off and I cover the window and I cover that window and there's no light getting in here, do you see anything? No, because they don't produce their own light, so there's nothing there to see with. Okay. Number two, what's the difference between visible light and television waves? Nothing. Well, there is one little difference. What's the little difference?
One is visible.
Their
One is visible.
their frequency or their wavelength. Okay, that's the only difference. Frequency or wavelength.
Just like I said.
And then third one, guys, as you're looking deeper and deeper into space, what are we seeing?
The reflection of the light.
Really old.
Technically seeing the past. Okay, technically seeing the past.
Yes.
I was totally right.
Huh?
Or sand.
Night vision goggles use infrared light. And so what they'll do is they'll put a flashlight, an infrared flashlight on the front. And so, I mean, nobody else can see that light because it's infrared, but that camera can pick that up because, so, you know, have you ever seen those new cameras they have? And those like a line of LEDs right around the outside? Those are infrared LEDs. And so they're lighting up the room, but you can't see it. And then that camera is,
Picking it up.
Huh?
Those come out.
yeah, they've had them for a while. But it'll be like a camera and like a line of lights around it.
Yeah, like
But,
finding Bigfoot and stuff. You know, dang well Bigfoot. Why you out there?